Okay, welcome to another video. So let us try to find out what is different parameters of this differential amplifier with a resistive load. So let us assume few parameters here. So let us assume VDD is equal to 0.9 volt and VSS is equal to minus 0.9 volt, and let me assume RD to be maybe 700 ohms, and let me assume WBL of first transistor as well as WBL of second transistor to be 25 as the ratio, and let us assume a tail current of 1 milliampere, and let us assume the resistance associated with the tail current as maybe 100 kilo. With these specifications, let us try to find out these parameters. So that is, what is the differential gain if it is measured single-ended, what is again the differential gain when it is measured differentially, what is common mode gain when it is measured single-ended, what is common mode gain if it is measured differential, and finally let us find out what is CMRR single-ended and what is CMRR when it is differentially measured. Okay, now let us write the equations for all these gains. So now we know that for differential amplifier there are two inputs. If both the inputs are different, so now here you can see it is VID by 2, and if it is minus VID by 2, I'm having equal amplitude but out of phase inputs, which will be a differential input. If I measure the output here, because of these two differential input, if I measure the output at V01 with respect to ground, so that becomes V01 by VID. So this is one of the differential gain. If you obtain the expression for this will be GM RD by 2. So this will be the expression for, of course it will be minus GM into RD by 2 if it is V01 by VID, which will be equal to this. Suppose this is there, it's also possible to measure V02 by VID. In such case it will be GM RD by 2. So there is no phase shift here. So this is GM into RD by 2. Now what is differential gain then? So differential gain is nothing but V02 minus V01 by VID, which will be actually GM into RD. This is the magnitude. And what is ACM? This will be equal to GM into, of course, minus GM into RD by 1 plus GM into 2 RSS, which you can approximately write it as equal to RD. You can take out GM as common factor, so that will become 1 over GM plus 2 RSS, or it can be further approximated as, of course it is minus RD by 2 RSS. So this is the common mode. Okay, this is common mode single-ended gain. When I say this is actually V01 by VCM. So when I apply inputs as VCM and VCM, when I say VCM, it is common mode signal. You can see I'm applying same type of signal to both V in 1 and V in 2. That's why I call it as common mode signal. So that is, I'll get the same expression for either you measure at this point or this point, the gain expression remains the same. So what is this? This is common mode differentially measured gain, which is nothing but V02 minus V01 by VCM. since both the magnitudes are same, if you take their difference, it will be 0. It will be 0. And we know that this is nothing but AD by AC. When I say it is AD by AC, it is differential gain to common mode gain. Since it is measured single-ended, you can say it as SE AC. So now it's actually GM RD by 2 divided by RD by 2 RSS. Suppose if you simply take the magnitude of these parameters, let me just take out this. So then what is this? It's actually GM into RD by 2 is your ADSC, and this is RD by 2 RSS. RD by 2 RSS. So this RD will go, this 2 and 2 will go. You will end up with GM into RSS as the CMRR single-ended. CMRR single-ended. So this will be the expression, and of course CMRR differential is nothing but ADD by ACMD. Since ACMD is 0 and this is GM into RD, this is actually infinite. These are the expressions for different gains at different points. So let us try to obtain the values of this. So I know that I need to find out what is ADSC. ADSC is nothing but, as per this, it is minus GM into RD by 2. So what is GM now? GM is given by under root of 2ID Kp W by L. Let me see. Yeah, this is fine. Let me find out the values. So let us now here we have assumed I is equal to, just have a look. The current assumed here is 1 milliampere. That's what is 1 milliampere. So since it's a tail current source, half, okay, ID1 ID2 will be half of this I, that is 0.5 milliamperes. So this will be equal to 2 into 0.5 milli, because we know that Kp is 200 micro. W by L is taken as 25 into 25. So let us find out what is GM is. It is under root of 1 exponential minus 3 into 200 exponential minus 6 into 25, close the parenthesis. Okay. So GM is 2.23 millisiemens. This is millisiemens. Of course, RD is given by 700 ohm. RD is given as 700 ohms. So naturally this becomes, this into 700 is 1.56 by 2. So it is 1.56 by 2 would be 0.78. So this is minus 0.78. So ADSE is minus 0.78. So this is the gain of the amplifier when it is measured single-endedly. So then what is ADD differential? It's actually GM into RD. It's actually minus GM into RD. When it is differentially measured, we actually have it as plus, because it is V02 minus V01. That's what is GM into RD. So this becomes actually 1.56 volt per volt. So this is AD differential measure. So let us try to find out what is common mode single-ended. So common mode single-ended, as we know that the expression is minus of RD by 2 RSS. RD by 2 RSS. Of course, that's what is the expression we have, RD by 2 RSS. So RD by 2 RSS happens to be, RD is of course, this is minus 700 by 2 into RSS is 100K. So this comes out to be 700 divided by 200 exponential 3. So it's actually minus 3.5 millivolt per volt. So this is the gain. So gain is very, very less for a common mode signal. Therefore, what is CMRR single-ended? CMRR single-ended is nothing but ADSE by ACMSE, which is nothing but, of course, take the magnitudes only. It is 0.78 by 3.5 milli. So it will be 0.78 divided by 3.5 exponential minus 3. You see it is 222.85 is the CMRR. So its capability of rejecting a common mode signal is 222 times. Similarly, what is CMRR differential? It's actually ADD by ACMD. ACMD is actually 0, so it's now 1.56. Naturally, this is infinite. This is infinite. So this way we can able to find out what is different parameters of the differential amplifier given the dimension and all other parameters. Okay, let us move on to active load amplifiers. So let me write the differential amplifier. This is differential amplifier with active load. This comes out to be this, and I have this is my tail current source minus VSS. This is VDD. This is E0. This is V in 1, V in 2. This is NMOS. This is again NMOS. This is PMOS. This is PMOS. Let us name it as M1, M2, M3, M4. This is again NMOS. So let us have some bias voltage. This is M5, and here this is the point where you take the single-ended output voltage. Let us assume Kp of NMOS transistor as 200 microampere per volt square. Let us assume Kp of PMOS as 100 microampere per volt square. Let us assume VTO of NMOS as 0.4 volt and VTO of PMOS as minus 0.4 volt. Let us assume W by L of 1 is equal to W by L of 2 as something like 25. Let us assume W by L of 2 is equal to W by L of not 2, it is 3 and 4 is equal to 50. Let us assume W by L of 5 as around maybe around 50. Let us just assume the values, and let us assume all the MOSFETs have lambda of 0.01 volt inverse. So this is the value of lambda. Let us consider a current of 1 milliampere here. So then actually ID, okay, current flowing through this arm will be 0.5 milliampere, and this will be again 0.5 milliampere because these two are balanced. So ID of all transistors except M5, so this is 1 to 4 will be 0.5 milliamperes. Now we are asked to find what is the differential gain, what is common mode gain, and then finally what is CMRR. So we know that the expression for the differential gain when two inputs are different is given by of course let us take only the magnitude. It is GM1 into R02 parallel with R04, and for this it will be equal to the expression for that will be equal to, of course you can take simply the magnitude of it, it will be 1 over 2 times RSS into GM3. When I say RSS, it is the tail current resistance. It is 1 over 2 RSS into GM3. And actually, what is this? So this will be GM1 R02 parallel with R04 divided by this means, okay, it will be multiplied by 2 RSS into GM3. So this will be the expression for CMRR. Let us try to estimate all these values of GM1, R0 and then GM3. So we know that GM1 is equal to under root of 2ID1 Kp W by L of first transistor. This is NMOS. Let us find out how much is this. Because we are assumed a current of 1 milliampere, here it is 0.5 flowing. It is 2 into 0.5 milliamperes multiplied by 200 micro into W by L. We have taken it as 25. This is 25. So what is GM1 then? GM1 is equal to, let me find out, it's under root of 1 exponential minus 3 into 200 exponential minus 6 into 25 close. So it is now 2.23 millisiemens. How much is GM3? So GM3 is nothing but 2 times ID3 Kp of P W by L of 3. Now it is again 2 into 0.5 milliampere multiplied by, since it is a PMOS transistor, this is now 100 micro multiplied by W by L of 3 is actually twice of it, so it is now 50. So here it is divided by 2, here it is multiplied by 2. So GM3 is also same as GM1, which is nothing but 2.23 millisiemens. Now we need to find out what is R01, which is nothing but 1 over ID1 into lambda 1. So since we know that these transistors, of course, M1, M2, M3, M4 will have same current of 0.5 milliampere and their lambdas are 0.01. Shall I say this is equal to R02 is equal to R03 is equal to R04 is equal to 1 over 0.5 milliampere into 0.01, because this is ID and this is lambda. If I go there, then it is 0.5 exponential minus 3 into 0.01. 1 over that is 200k. This is 200 kilo ohm. So this is my R0 to R04. So let us find out what is RSS. RSS is nothing but the resistance looking down here, which is nothing but R05. This is R05, which is nothing but 1 over ID into lambda 5. So this ID is actually 1 milliampere. So that will be actually, here when the current becomes twice, that will actually become 100k. This is 100 kilo ohm. So this is now RSS is 100k, and we have all other parameters. Now these are the things what we have to find out. Let me substitute here only. What is this now? ED. ED magnitude is GM1 into R0 parallel. Okay, GM1 is 2.23 milli multiplied by how much is R02, R04, R0. Okay, all the resistances are 200k. 200k in parallel with 200k will become 100k. So this is now 100k. So k and milli will go off, and you end up with 223 volt per volt as the gain of the differential gain of this active load amplifier. So this is 223 is the gain of this. If you want to find the what is the gain of this, it's actually, so what is RSS? RSS is actually 100k. RSS is 100k. GM3 is 2.23. So let us make it 2 into RSS is 100 exponential 3 into 2.23 exponential minus 3. So it's so this is now 2.24 millivolt per volt. The gain is actually 2.24 milli is the gain. Volt per volt is it's a unitless quantity. So this is the expression. Of course, what we have to do is to find what is CMRR, as we know that CMRR is nothing but AD by ACM. So AD by ACM. If you do 223 divided by 2.24 milli, so you'll get the CMRR, or if you multiply this, you'll get the same value. So what I'll do is, I'll just do this. Okay, now 223 divided by 2.24 exponential minus 3, which is now, let me just do it, it is CMRR is 99.5 into 10 power 3. So this is my CMRR. It's a very large value, almost 100k, which is true here also. So if you multiply these things, you'll get the same value. So this way we can able to find the parameters related to this active load differential amplifier, provided you know the dimensions of the transistor and their lambda value and the current flowing through that. And if you know the equation for your differential gain, common mode gain and CMRR, we can able to estimate the values. So here differential gain is 223 and common mode gain is very less, so CMRR is almost 100k. Thank you.